Man has always depended upon the earth to provide his food, clothing, and shelter. Urban living has removed most of us from immediate contact with the source of the raw materials we need to exist, but the dependency is still there. Without the minerals and rocks of the earth, life as we know it would cease to be. We still depend upon minerals and rocks for our automobiles, our food, and even our homes. If you examine the rocks in the foundation of this house, even just casually, you'll notice that they look quite different. Obviously, they're different colors, and where this rock has a more uniform color, this one has a more speckled or mottled appearance. The rocks are different. They're composed of different materials. The materials that rocks are composed of are minerals. So minerals are the fundamental building blocks of rocks, and therefore the fundamental building blocks of the earth. In this program, we'll look at those materials we call minerals and rocks. We'll show you how to tell them apart, and we'll start you on the road to identifying them. Then we'll return to this house and show you some of the ways minerals and rocks can be used. There are several methods or techniques of identifying minerals. We'll talk about one of the most common methods, and after we've examined minerals, we'll look at rocks and show you how rocks are identified. The characteristics of a mineral that we see or determine when we examine a hand specimen closely are the physical properties of that mineral. There are a number of physical properties that are commonly used to identify minerals. At this time, we'll consider 5 of the most useful properties: color, luster, hardness, cleavage, and crystal form. The color of a mineral is a physical property that's readily apparent to the casual observer, but unfortunately it's not always a useful property simply because some minerals occur in many different colors. Unless a mineral occurs in a single distinctive color, we cannot use it reliably to identify the mineral. Much more useful than color is the property of luster, which is the appearance of a mineral in reflected light. Of these 2 specimens, one looks like it's made of metal. The other would never be confused with a metal. We say that this specimen has a metallic luster and this mineral has a non-metallic luster. All minerals have either a metallic or a non-metallic luster. The hardness of a mineral is also a physical property. This mineral is quite soft. I can scratch it with my fingernail. In contrast, this mineral is so hard that it will scratch glass. Hardness is measured on a scale of 1 to 10. My fingernail has a hardness of about 2.5 on that scale. Glass is about 5.5, and diamond, the hardest mineral of all, measures 10. Some minerals have a tendency to always split along definite planes. This property we call cleavage. Although not all minerals have cleavage, some minerals cleave or split in more than one direction. A common mineral everyone knows is table salt. Salt is the mineral halite, and it cleaves in 3 directions. Here's a specimen of halite large enough to see all 3 cleavages. They meet at right angles, which gives salt the appearance of being cubes. Minerals may cleave in 1, 2, 3, 4, or 6 directions, and the directions of cleavage may intersect at right angles or at some angle other than a right angle. Whatever cleavage a specific mineral has, it's important to realize that that mineral always exhibits the same cleavage. A very important physical property of minerals is crystal form, the shape they assume when they crystallize. The ions in the mineral have a definite arrangement or pattern which gives the mineral its external crystalline form. Halite and many other minerals crystallize as cubes. Some minerals crystallize as 8-sided geometric forms called octahedra. There are many different possible crystal forms that minerals may have. But the important point is that all minerals are crystalline, and the crystallinity is a physical property that can be used to characterize minerals. There are other physical properties, but these will be enough to show you that when we use the term mineral, we are referring to something very specific. If we speak of halite, only one mineral will have all of the characteristics or properties of halite. If the properties of a specimen are different, then the specimen would not be halite. There are several thousand different minerals, and it's handy if we can classify them into groups. Although minerals can be classified in various ways, a widely used classification is based upon the chemistry or composition of the minerals. For example, an important group of minerals are compounds of oxygen. These we call oxides. Two important iron oxides, hematite and magnetite, are important minerals used to make steel. The yellowish-brown rust that forms on iron and steel tools when they're left out in the weather actually is a mineral, limonite, another iron oxide. Some minerals are compounds of sulfur. These we call the sulfides. Several important minerals used in industry are sulfides. Galena, the principal source of lead, and sphalerite, mined for zinc, are both sulfides. The mineral gypsum, which is widely used in the making of sheetrock for walls, is a sulfate mineral. That is, a compound containing sulfur and oxygen. Another important group of minerals are compounds involving carbon and oxygen. These we call carbonates. The mineral calcite is a very common carbonate. It's the major component in the rock limestone, the principal ingredient in making cement. A large and important group of minerals are the silicates. These are compounds of silicon and oxygen. The very common mineral quartz is a silicate. The silicates also include such diverse minerals as the feldspars, the mica minerals, biotite and muscovite, the pyroxenes, and amphiboles. Silicate minerals are all around us. We could not live without them. The soil upon which we depend for food is composed primarily of clays, which are also silicate minerals. Although some of the silicates have important industrial uses, they're important to us at this time because most of the Earth's rocks are composed of silicate minerals. They're the most abundant minerals in the Earth's crust. Minerals form in many different ways. Some form by the cooling and crystallization of molten rock material within the Earth. Others form from gases around volcanic vents. Still others form by precipitation from seawater or by evaporation of saltwater lakes. Some minerals may be precipitated by groundwater moving through the rocks. As we said at the beginning, rocks are composed of minerals. They're simply aggregations of minerals. The great variety of rocks depends upon the minerals present and upon the conditions under which the rock formed. All rocks exposed at the Earth's surface can be classified as igneous, sedimentary, or metamorphic rocks. This diagram shows the relationship among the three major groups of rocks. Igneous rocks form by the cooling of molten magmas that often rise from the mantle into the crust and often flow out onto the surface as lavas. Sedimentary rocks are composed of the weathered and transported fragments of older rocks. Metamorphic rocks are formed by the heating and compression of older igneous and sedimentary rocks. It really isn't difficult to tell the difference between the three rock groups. Because igneous rocks once were molten, they are composed of crystals, and the crystals have a tight interlocking arrangement. Most of the sedimentary rocks, on the other hand, are composed of fragments or pieces of minerals or other rocks. If we see crystals, they generally are broken and incomplete. And because sedimentary rocks are formed by deposition of material, they generally are layered or stratified. The igneous rocks are composed of silicate minerals. Fragments of those silicate minerals may be present in sedimentary rock, but there may also be present low-temperature minerals such as the carbonates, sulfates, and oxides. The metamorphic rocks at first glance may look a lot like igneous rocks. They are principally silicate minerals. But if you look closely, the rock may seem to have a layered or banded appearance. Because metamorphic rocks were subjected to pressure, the minerals assume a parallel arrangement that gives metamorphic rocks this distinctive banded appearance. Now, let's look more closely at each of these groups of rocks, beginning with igneous rocks. As the molten parent material of igneous rocks, called magma, cools, mineral crystals form. The slower the rate of cooling, the larger the size of the crystals, and the rate of cooling would be very much controlled by where the cooling took place. The size and arrangement of crystals in the igneous rock is referred to as the texture. The texture tells us a great deal about the cooling history of the rock. If the molten material cooled at the surface, the rate of cooling might have been so rapid that there was insufficient time for crystals to form. Now the rock would have a glassy texture, and we would be unable to recognize any individual crystals. Magma originates at great depth. Probably much of it forms in the mantle and forces its way upward into the crust, where it may be stored in a magma chamber, and cooling begins. The magma chamber is well insulated by surrounding rock, and cooling in the chamber will proceed slowly enough to allow minerals to crystallize. If the partially cooled magma were now to be erupted onto the surface, more rapid cooling would occur, and the resulting rock will show the early formed larger crystals surrounded by smaller crystals. This is how such a rock would look under a microscope. The larger crystals, called phenocrysts, are surrounded by a matrix of smaller crystals formed after the magma moved to the surface. This rock texture is called a porphyry and indicates the rock experienced 2 stages of cooling. But if the magma cooled deep within the earth, the rate of cooling would be very slow, allowing very large crystals to grow. When the magma has completely cooled, the texture of the rock will show an interlocking system of large crystals. We would say that such a coarse-grained igneous rock has a phaneritic texture, as seen in this microscope view. Now, if we combine the texture of the rock with the minerals present, we have a basis for naming or classifying igneous rocks. For example, a rock that is high in silica, that is composed mainly of feldspar and quartz, and has mineral crystals large enough to see without a microscope, we would call that rock a granite. On the other hand, that same mineral composition in a rock with mineral crystals so small that we would need a microscope to recognize them would be called a rhyolite. A rock that has low silica minerals like the amphiboles and pyroxenes, and a very low silica mineral called olivine, and mineral crystals large enough to see with the naked eye, that rock would be called a gabbro. A rock with that same low silica composition but microscopic crystals would be called a basalt. Igneous rock that cools so rapidly that it has a glassy texture would be called an obsidian, regardless of its composition. Igneous rocks that form deep within the Earth's crust are often later exposed at the surface by uplift and erosion. The weathering of the overlying rock material and its removal by streams, by wind and glaciers provides the rock debris for sedimentary rocks. The sedimentary rocks are a bit easier to identify. For the most part, they fall into either of 2 large subdivisions. Most sedimentary rocks are formed of fragments, bits and pieces of pre-existing rocks. The fragments are derived from the erosion of the continents and are carried along in streams as boulders, sands, and muds to the sea, where they're deposited in a variety of environments. Rock debris the size of gravel is deposited where the currents are strong and the energy is too powerful to allow the smaller particles of sand and mud to settle. The sedimentary rock formed of gravel-sized material is called a conglomerate. In areas where the water moves more slowly, a lower energy environment, fine particles are deposited on the seafloor. Most of this material eroded from the land is deposited in relatively deep water. Moving away from the coastline, the seafloor naturally gets deeper. Water energy is reduced, and the current velocities become less and less. As the water slows down, the sandy particles are deposited first, and farther out to sea, in quiet, deep water, the very fine mud particles settle out. With time, the sediments become thicker, and they become compacted and hardened. The sands become sandstones, and the muds turn to shales and mudstones. Other sedimentary rocks are formed by precipitation from solutions. The specific name given to each of these depends upon the principal mineral present. If the rock is composed principally of the mineral calcite, we call the rock a limestone. However, if the rock is principally halite, the rock is called rock salt. And if the mineral is gypsum, the rock is also called gypsum. The igneous and sedimentary rocks that we have been discussing may be so intensely heated and squeezed within the earth that the minerals and textures actually undergo changes. This is metamorphism. Let's now look at the metamorphic rocks, the last major family of rocks. The great heat and pressure of metamorphism may produce a parallel arrangement of minerals in metamorphic rocks, but the heat and pressure may also cause new minerals to form and other minerals to recrystallize. This change from the original rock may be very slight, or it may be so great that we see few or none of the characteristics of the original rock. If the metamorphic rock has a distinctive parallel arrangement of minerals, we say the rock is foliated, but metamorphic rocks may be foliated or non-foliated. Among the foliated metamorphic rocks, several names are used depending on the degree of foliation. If the foliation bands are rather broadly spaced and the rock is coarsely crystalline, we would call the rock a gneiss. But if the foliation is very fine and the rock is composed principally of minerals like the micas, we would call that rock a schist. If a non-foliated metamorphic rock is composed of crystalline calcite, we would call it a marble. Marble is simply metamorphosed limestone. And if the rock is composed solely of quartz, it would be called a quartzite. Most quartzites are formed by the metamorphism of a quartz sandstone. One other interesting metamorphic rock should be mentioned. When a shale undergoes metamorphism, the clay minerals that compose the shale are reoriented by the pressure, and the rock splits very easily across the bedding planes. The rock is now a slate, and because slate does split so readily along smooth surfaces, it's very useful for blackboards, roofing, and hearthstones. During most of this program, we've been considering some of the features of minerals and rocks that allow us to recognize them in nature. We looked first at minerals and the physical properties of color, luster, hardness, cleavage, and crystal form. These are not the only physical properties that can be used in the identification of minerals, but these will serve to show you that minerals have rather definite characteristics that permit us to tell one mineral from all other minerals. These 5 properties will also serve to get you started identifying minerals. We also attempted to bring some order into the thousands of minerals that occur in nature by presenting a system of classification based upon the chemical composition of minerals. In this system, we may group minerals into oxides, sulfides, sulfates, carbonates, and silicates. There are additional groups, but these are the most important and are enough to demonstrate that a classification based upon chemistry is a valid way to classify minerals. Next, we looked at rocks, which are really just aggregations of minerals. The origin of the rock determines the type of rock: igneous, sedimentary, or metamorphic. Igneous rocks originate from molten magmas that cool either slowly, forming relatively large crystals, or rapidly, forming relatively small crystals. The size of crystals or texture and the mineral composition provide a basis for naming igneous rocks. Sedimentary rocks form at or near the surface of the earth from the debris of pre-existing rocks. Those sedimentary rocks composed of fragments of pre-existing rocks are named according to the size of the particles, but those that precipitate from solution have names that depend upon the principal mineral present. Metamorphic rocks form at depth as the result of older rocks being subjected to great heat and pressure that change the original textures and minerals. The names given to foliated metamorphic rocks depend upon the texture of the rock. The names given to non-foliated metamorphic rocks depend upon the minerals present in those rocks. Now, let's return to the field and examine a few rock specimens, and then look at some of the places right around you where rocks and minerals are used in your daily life. As we walk about in the field to gather rock specimens, we usually look at natural exposures of rock, but we can also go to slopes where rock debris tends to accumulate, to gravel deposits along streams, and even to man-made exposures like road cuts. To get a good look at the rock, I'll use a rock hammer to expose a clean, unweathered surface. Then I can use a hand lens to look closely at the texture and to see what minerals are present. Obviously, these two rocks are very different, so let's use what we've learned to identify them. In this rock, the texture is rather uniform, with very fine-grained mineral crystals forming a dense interlocking arrangement and composed of biotite, amphibole, feldspar, and very little quartz. So the texture indicates that this is an igneous rock. The low silica composition and extremely fine-grained texture indicates that it's probably a basalt. What's most apparent about this specimen are the alternating light and dark layers. The light layers are composed of clear quartz and white and pink feldspar in a coarse-grained interlocking arrangement. The dark layers are composed of tiny biotite mica flakes oriented parallel to each other and to the banding. This parallel orientation of the minerals that forms this banding indicates that this is a foliated metamorphic rock. On the basis of the wide spacing of the bands, I would classify it as a gneiss. Over here we see an outcrop of still another kind of rock. This bed is composed of rather loose sand grains, rounded pebbles, and still larger cobbles of what appear to be porphyritic igneous rocks, among others, and the bed is crudely stratified. So this is obviously a sedimentary rock, and the great range in grain sizes indicates that it's a conglomerate. Well, now we've identified several rocks in the field, but why is this so important? Well, let's go to a typical house and see how some of these rocks are actually used. You may be surprised at some of the ways metals and minerals are used right in your own home. Let's take a walk through this house, which is partly under construction, and look at some of them. This walkway is made of concrete, which contains sand and gravel aggregate bonded together by cement, which is made from limestone, shale, silica, gypsum, and iron. The rest of this walkway is made of slabs of natural sandstone. This is crushed marble used for decorative stone. Back in the foundation of the home, various rock types are set in place with concrete or mortar. Just look at all the materials needed to build your house. Not one of them would be possible without the minerals, rocks, and metals inside the earth. Let's look at some of the specific applications. The fiberglass insulation used in your attic is made from melted quartz or silica sand. The glass fibers have a very low heat transfer, are lightweight, low cost, and fireproof. The filament in this common light bulb is made of the metal tungsten, which has a very high melting point and can resist the extreme temperatures generated by electrical current. And it gives off a bright, steady light. All of the wiring in your home now is made from the metal copper, which is an excellent conductor of electricity and can be made easily into wire. So these are just a few examples of the many ways rocks and minerals are used just in building your home. Now, think of all the metals and non-metals you probably use in furnishing your home with appliances like your television, telephone and refrigerator, china, tableware, pots and pans, and of course your automobile. If it seems like rocks and minerals are everywhere and in practically everything you use, you're right. The amount each of us uses every year is quite surprising. Nearly 1 ton of metals, over 11 tons of rocks and non-metals, and energy equivalent to about 14 tons of coal. That's a total of over 26 tons of rocks and minerals for every person every year. So, whether you're working or just relaxing, remember that to use and enjoy all the items around your house, raw materials first had to be mined and processed, smelted, refined, and fabricated into final products. But before that, a rock or mineral had to be identified and classified according to its composition and physical properties. So yes, we do depend on minerals and rocks for practically everything. You can earn college credit by enrolling in the Earth Explored television course. For information on the course, contact the Adult Learning Liaison at your local public television station.